Welcome to Descriptive Statistics. Today, we are going to explore the definition and scope of statistics. If you have ever looked at a massive spreadsheet of numbers and felt completely lost, you are in the right place. We will learn exactly how to turn that chaos into a clear, understandable story that drives real-world decisions. Let us start by imagining you are the manager of a large supermarket. Every single day, thousands of customers buy tens of thousands of items. If you just look at the raw receipts, you will see a massive, confusing mountain of numbers that tells you absolutely nothing. You would not know if you are making a profit, which items are selling out, or what to stock up on for next week. Statistics is the ultimate tool that takes this chaotic mountain of raw numbers and turns it into a clear, understandable story. It is like putting on a pair of magical glasses that lets you see patterns hidden inside the chaos. Now that we understand why we need it, let us look at the formal definition. Statistics is the scientific discipline that deals with the collection, organization, presentation, analysis, and interpretation of numerical data. Let us break that down into simpler pieces. First, collection means gathering the raw facts, like asking 100 people who they will vote for. Next, organization and presentation mean putting those facts into neat tables or graphs so they are easy to look at. Finally, analysis and interpretation mean doing the math to find the hidden meaning and explaining what that math actually tells us about the real world. This step-by-step process of making sense of data did not appear overnight. The history of statistics is a fascinating journey from simple counting to advanced artificial intelligence. In ancient times, around 3000 BC, empires like Babylon and Egypt used basic statistics simply to count their citizens, measure land, and track food supplies for taxation. By the 17th century, scholars began using probability games, like rolling dice, to develop the first mathematical rules of statistics. In the 19th and 20th centuries, pioneers like Carl Pearson and R.A. Fisher created the modern formulas we use today. Today, statistics has evolved into the backbone of data science and machine learning. As statistics evolved, it split into two massive branches that we use today: descriptive statistics and inferential statistics. Descriptive statistics is all about summarizing and describing the data you already have in your hands. If you calculate the average test score of your class, you are just describing that specific group. Inferential statistics, on the other hand, is about making predictions or guesses about a massive unknown group based on a tiny known group. For example, if you taste one spoonful of soup to check if the whole pot needs more salt, you are using a small sample to make an inference about the entire pot. Before we move on, let us see this divide visually. On the left side of this diagram, we see descriptive statistics. Notice how we have a known group of people and we are summarizing their data using bar charts and pie charts. We are just describing what is already there. On the right side, we have inferential statistics. Here, we take a small sample, represented by the people inside the magnifying glass, and we use them to make a prediction, shown by the green arrow, about the massive, faded population in the background. This is the leap from known to unknown. Now that we have seen the big picture, let us dive into descriptive statistics by looking at its most fundamental tool, the arithmetic mean, commonly known as the average. The mean takes a whole group of different numbers and finds a single central number that represents the entire group fairly. We calculate it by adding up all the individual values we collected and then dividing that total by the number of values we have. It is the mathematical equivalent of putting all the values into a single bucket and sharing them equally. This brings us to the mathematical formula for the mean of a sample. Let us break down every symbol. The symbol x bar represents the sample mean, which is the average value we are trying to find. The large symbol is the Greek letter sigma, which simply means add everything up. The variable x sub I represents each individual data point we collected, and n represents the total number of data points in our sample. So the formula literally translates to add up all your individual numbers and divide by how many numbers you have. If the total sum of the values increases while n stays exactly the same, the mean will also increase. Now that we have our formula, let us see this with a concrete example. Suppose you are a teacher and you want to find the average score of 5 students who recently took a mathematics quiz. The scores out of 10 are 4, 6, 8, 7, and 5. We need to find a single number that represents the overall performance of these 5 students. This will help us understand if the class is struggling or doing well as a whole. To solve this, we will first identify our total number of observations. Since there are 5 students, our n is equal to 5. Continuing with our calculation, we need to find the numerator of our formula. We do this by expanding the summation part. We take each student's score and place a plus sign between them. This step gathers all the raw data into one combined total. By adding the numbers 4, 6, 8, 7, and 5 together, we find that the total combined score of all 5 students is 30. This is the total value that we now need to distribute evenly across the 5 students. If every student had scored exactly the same, this total would still be 30. We are now ready for the final division step. We substitute our total sum, which is 30, and our total number of students, which is 5, back into the main formula for the mean. This division step is what actually calculates the average. We are essentially asking how much each student would get if the total score was shared equally. 30 divided by 5 gives us 6. This means that on average, the student scored a 6 out of 10 on the quiz. Because we only calculated this for the 5 students we actually tested, this is a perfect example of descriptive statistics. Now let us look at how inferential statistics works using a slightly different scenario. Imagine a factory produces 10,000 light bulbs every day, and the manager wants to know the average lifespan of these bulbs. It is impossible to test all 10,000 bulbs because testing them means leaving them on until they burn out, which would leave the factory with nothing to sell. Instead, the manager must use inferential statistics. They decide to randomly select a small sample of just 100 bulbs from the daily production. They test these 100 bulbs and find that their average lifespan is 1,200 hours. The goal now is to use this small sample to make a confident guess about the entire population of 10,000 bulbs. This is the exact moment where we cross the bridge from descriptive to inferential statistics. In this expression, the symbol mu represents the true population mean, which is the actual average lifespan of all 10,000 bulbs that we cannot directly measure. The wavy equal sign means is approximately equal to, and x bar is the sample mean that we just calculated. This formula shows the core logic of inferential statistics. We use the known sample average to estimate the unknown population average. Let us apply this powerful mathematical leap of faith to our factory problem. By substituting our sample result of 1,200 hours into the formula, we estimate that the true average lifespan of all 10,000 bulbs is approximately 1,200 hours. We did not have to test every single bulb to find this out. By carefully analyzing a small, manageable sample, we successfully predicted the behavior of a massive, unknown population. This saves the factory immense amounts of time and money while still providing highly accurate information. This ability to predict and analyze is why statistics is so crucial today. The scope of statistics extends far beyond simple averages and into the cutting edge of modern technology and global problem solving. In the tech industry, companies use a statistical method called A/B testing to decide which website design makes users click more often. In healthcare, statistics allowed scientists to track COVID-19 infection rates and prove that new vaccines were actually effective. Furthermore, the entire field of artificial intelligence and machine learning is just advanced statistics using massive amounts of data to predict the correct answer. We have covered a lot of ground today, so let us summarize the most important ideas. First, statistics is the powerful science of collecting, organizing, and interpreting data to make informed decisions. Second, we use descriptive statistics to paint a clear picture of the data we already have, turning messy numbers into neat summaries, like averages. Finally, we use inferential statistics to take a leap of faith, making highly accurate predictions about vast unknown populations. Whether you are managing a small business or training an advanced AI model, you now understand the essential tools to find the truth hidden inside the numbers.